Ant colony optimization stems from the field of swarm intelligence. Swarm intelligence is the collective behavior of decentralized, self-organized systems that are either natural or artificial. Examples of swarm intelligence are schools of fish, hives of honeybees, and colonies of ants. Today, we are going to learn about ant colony optimization. We will cover what ACO is, why it works, and its applications. Ant colony optimization, or ACO, is inspired by the foraging behavior of ant colonies. ACO is a set of algorithms developed from ants' ability to find the shortest path. These algorithms can be applied to challenging combinatorial optimization problems. Ant colonies are types of social insect societies. These colonies consist of simplistic individuals and yet are able to perform incredibly complex tasks such as division of labor, territory defense, and foraging. They are able to achieve these incredible feats by coordinating their actions through stigmergy. Stigmergy is a type of indirect communication where an agent chemically modifies the environment in order to stimulate the next agent to perform an action. An example of stigmergy is when a foraging ant, an ant that is collecting food, leaves behind chemicals that increase the chance of other ants taking the same path. So how exactly do these creatures with limited visual ability and mental faculty communicate? They do so through pheromones. Ants leave pheromones wherever they walk. When ants sense these pheromone trails, they can follow them to food found by other ants. These pheromones serve as directions. One important quality of pheromones is they evaporate over longer periods of time. This affects which paths the ants take. Excellent examples of ants placing and following trails of pheromones are the double bridge experiments, which were executed by Denneberg, a professor at the Université Libre de Bruxelles, and colleagues. It is important to note that in these experiments, pheromone evaporation is negligible due to the short time frame. In the first of these experiments, the researchers set up 2 bridges, each of equal length. The bridges connected the ants' nest to a food source. At first, the ants crossed both bridges with equal probability. However, due to random fluctuations, one bridge began to be crossed by more ants than the other. This, in turn, led to a higher buildup of pheromones, which resulted in more ants crossing that bridge. When a large number of ants cross a certain path, the more pheromones are laid. The higher pheromone presence leads more ants to develop a bias and take that path. Eventually, nearly all of the ants converge on the same path. This process is called positive feedback and is the self-organizing behavior of ants. However, not all paths are created equal. In the second experiment, one bridge was twice as long as the other. When the ants first started their journey from the nest to the food source, they had to decide between the long or the short bridge. The bridges appeared to be identical and therefore had an equal probability of being crossed. However, the ants who randomly chose the shorter bridge arrived at the food source sooner and started their return to the nest sooner. The ants who chose the longer bridge took longer to get to the food and longer to return. This longer journey resulted in the lower presence of pheromones because there was not enough time to take the journey twice. The following factors affect which bridge the ants take: bridge length, time duration, and pheromone presence. With these in mind, which bridge do you think the ants are going to take? The shorter one. The shorter bridge is traversed by ants more frequently and in a smaller time period. This resulted in a heavier pheromone presence. When the ants were faced with the decision of which bridge to take, they favored the shorter one because of the higher presence of pheromones. This led all of the other ants to eventually choose that path. Ant colony optimization is based on probability. As we saw in the second experiment, the ants started with equal probability of taking the two bridges. Then the higher pheromone presence in the shorter bridge increased the probability of ants taking the optimal route. Eventually, all of the ants converged onto the shorter bridge. This probabilistic model is the root of all ACO algorithms. In the real world, ants are not given two bridges. They have to find a path on their own. When a colony creates a path to a food source, it is not necessarily the shortest path. However, an ant will wander off and stumble upon a shorter route. Due to pheromone evaporation, there is a greater probability that the rest of the ants will take the shorter route due to the higher presence of pheromones. The presence of pheromones, or lack thereof, keeps the balance between exploitation and exploration. Exploration is needed to find the shortest path, but exploitation is needed to utilize the optimal path. Ants are able to find the near optimum path from the nest to the food source. This is the inspiration that catapulted ant colony optimization into existence. It is from the incredible field of ant colony optimization that profound applications have originated. These applications include, but are in no way limited to, the traveling salesman problem, vehicle routing, and adaptive online education. We will explore how ACO is applied to adaptive education. In order to create a personalized and effective curriculum for a student using an online learning program, there are two factors that are taken into consideration. One is choosing the curriculum, background, and learning style of an X learner similar to those of the targeted learner. Second is that the targeted learner's past and performance are taken into account and computed separately from the X learner. ACO is applied to the second issue. Learners are treated like ant agents. Imagine they traverse a learning path and deposit pheromones along the way. The amount of pheromones deposited is determined by one of two things. One, the frequency of which a path or subject was traversed. Or two, the learner's performance on the subject. When the e-learning system decides how to proceed from the completed subject, it takes into account the amount of pheromones deposited on previous paths. The higher probability of a path being chosen is proportional to the amount of pheromones deposited on previous paths. This aids in determining the tailored, optimal path for the targeted learner. Ant colony optimization is revolutionizing the way we solve problems, one ant at a time.